is the guided homework of a simultaneous multiple regression using SPSS. And the subjects we're studying is on infected humans who will become zombies. So our causal model is, what are factors will predict the amount of time left before an infected human becomes a full-on flesh-eating zombie? The detailed question of this guided homework is, in the earliest days of the post-zombie era, data was collected by the Alliance Center for Disease Control from 254 infected humans who had managed to reach the safety zone. The director of the CDC and her team are desperately trying to develop a prediction system that would accurately inform the safety zone medical personnel as to how long it will take an infected human to become a full-on zombie. The scientists who are looking for a cure for the zombie infection have very limited time and resources. And if they knew how much time each infected person had left, that information would be a critical piece of accelerating the development of a cure. So from the data collected, we identified that our predictor 1, which was the IV1, is the stages of zombieism. So look at the right side of the picture, and that's how each stage is described and explained. So stage 1, that is a normal human being, who got uninfected. Stage 2, primary infection. So look at his face. He's already got tired. Stage 3, secondary infection. Now he's a little bit hungry. And plus, you can see that he never washed. And he's got a little bit pale. So stage 4, the tertiary infection. So if you look at this guy, he's almost gonna be there. Become a zombie. And stage 5, there we are, our full-blown zombie. And we also find another predictor, which is predictor 2, that was also the IV2, which is the number of days outside of the safety zone. And lastly, we have the criterion, which is also the DV. The things that we wanted to predicting on is the number of remaining days of being human. Of course, it's for the infected. Next, we run a simultaneous multiple regression analysis using Excel data that collected by the Alliance CDC department, so we can answer the questions below. So as you can see here, this is the Excel sheet of our guided homework of the multiple regression. And remember, that is the raw data, which means we haven't do anything with the data screening or cleanup or analysis. So as you call that, this is the number of days outside of the safety zone, which is our predictor 2 or IV2. It's right here. And the next IV is a scale of zombieism. It's between 1 to 5, and you can find it right here. And lastly is our DV, which is the criterion, is the remaining days of being human. So you can find it right here. So which means the data is matching with the questions or the predictors and the criterion that we're trying to study for this multiple regression model. And another important thing for you to know is that all the predictors and the criterion are continuous. Continuous means their scale, they are just counting numbers, which means you can see the numbers here, like they're counting numbers, and that's continuous variables. So we can use them in the multiple regression, and that is also a critical issues that you need to always remember. When you run a multiple regression, you have to make sure your predictors and criterion are continuous variables. All right, after we make sure that that is the data that we're going to be using to analyze our multiple regression model, so we're good to do the questions from now on. So question 1, what are the IVs and DV? That is pretty much an obvious question, and I believe it's probably the simplest questions that we can answer because the answer is right about here. So the predictor 1 is the IV1, is the stages of zombieism, and the predictor 2, which is also called IV2, are the number of days outside of the safety zone. And our criterion, which is the DV, is the number of remaining days of being human for the infected. So you can just either copy and paste the answers right here, or you can just type them in. So question 2, what is the sample size? Is it large enough to satisfy statistical power and accuracy of a multiple regression model? So this question actually won't be that easier to find like we do for the question 1, but it's also not that hard. So here, sample size is the number of participants or objectives or participants or subjects that you have in your study. So we just need to find out how many people we have in the study. And actually, if you do go back to the beginning of the questions, we have one numbers here. Says that Alliance Center of Disease Control, they got the data from 254 infected humans. But whether we can use these numbers, well, we have to see. Because why? We need to check our Excel datasheet to make sure that we do have 254 people's data or information that listed here. And unfortunately, it's not easy to find it because our data started listing at row number 6. So it's going to be a little bit hard for us to identify how many people we have in here in this Excel data sheet. So the easiest way to do is we can create what we call an ID, and we can list them out as 1, 2, 3, 4, 5, etc., etc. So let me just do it quickly. Hold on. All right, so after we make the ID on the right side here, and we find out actually we only have 250 people. And actually, this is the true sample size we're going to use for the multiple regression model analysis. So you're probably going to be concerning about whether there is a difference. Why, in the questions we set 254, however, in the Excel sheet, we only have 250. So here's the thing. In your data analysis, sometimes you may have these issues happening. You did the plan to collecting this much of data, however, you may end up having less data. And let's just say because we do have limited time and resources. So we probably either have 4 zombies, unfortunately, 4 infected humans, unfortunately, either died or deceased. We don't know. So sometimes there be some ignorable data that could be missing that we easily gonna be hardly to find out or investigate it. Especially this is kind of a post-zombie era. Remember, it's scary and panic. We don't have time to really struggling on 254. So this could be actually a good notification for all of the researchers, especially when you do your research or dissertation. You may end up getting some numbers that is not what you planned for at the beginning. But don't get panic, because if you do have these kind of issues happening, remember, always go to the sample size you have for the actual data. So that's what we call consistency. Because how many number data you have is the honesty and consistency that you can reflect it on your multiple regression analysis. So no matter what you talked about earlier before, you just simply add a sentence here saying that, however, it turns out we only have 250 infected humans we're going to be studying on. So you can always make modifications in your research questions or literature review or your research design sections for your dissertation or research project. So we know that our sample size is going to be 250, and that will help us to answer the question 2. Okay, since our sample size is going to be 250 instead of 254, and we just need to add that rationale sentence to make sure that we do have 250 sample size as consistency with the research questions we pull up here. So here's the sentence we add. So we say, however, the CDC find out that 4 of these infected humans were suddenly turned into full-on flesh-eating zombies and had to be destroyed. Yeah, sad. Leaving the final count at 250. So the first part of question 2 we'll be able to answer right now. And so the sample size is going to be 250. Okay, the second part of question 2 is that, is this sample size large enough to satisfy statistical power and accuracy of a multiple regression model? As we all learned, actually a minimum sample size required for a multiple regression model for a statistical power of 0.8 will be 50. And actually, that will also give us a good estimated effect size after we do conduct a multiple regression analysis. So 250 obviously is bigger than 50. So which means we answer also the second part of the question too, is that it is large enough to satisfy the statistical power and accuracy of a multiple regression model. Proceed. Question 3. Did the data violate the assumption of normality? So this question will be answered by using SPSS. So next, I'm going to show you guys how to transfer the data from the Excel sheet to a SPSS program. So after opening up a SPSS program from your computer, then you can open up a new file, and it will be showing like this. And then you can just simply copy the data from your Excel sheet to the SPSS program. And remember, when you copy the data from Excel sheet, just do the numbers because SPSS cannot take the label of the variables from here. And I'll show you guys how to name the variables in SPSS later. So first of all, let's do the number copy and pasting from Excel sheet to the SPSS program. Okay, so I'm done with copying from the Excel sheet right here. As you can see, it has been flashing. That means the data has been selected here. So you go to SPSS and then just left click on here, make sure it's highlighted as yellow, and right click and just simply hold go paste. And there is our data successfully copying from Excel sheet to the SPSS program. And we just want to make sure double check the number, and that is 250, which means we got all the data in with no mistakes or errors. So this is actually the data view of the data that we just successfully copy and paste from Excel sheet. So if you see actually at the bottom of the SPSS program, you're going to see data view here. So actually if you go to variable view, that's how you switch the windows, and that's how you see our variables. So I'm going to show you later how to name the variables here into our true name of the predictors and the criterion of our regression model. Because we cannot call them var 0001, they have to be something that to do with zombies. Remember our zombie fancy variables. Alright, so next I'm going to show you how to name or rename the variables here. And the easiest way to do it is just we go back to our guided homework Word document. And here's all the names. Ta-da! So you just type them in. And remember, so in SPSS, there's one little tiny instructions. So you cannot have spaces here. So to replace the spaces, you have to use an underscore to connecting all the words that you have here. So when you type them in, make sure you put an underscore instead of a space between the words. And also remember, make sure it is the right variables you're typing the right name in. So for example, if you go variable 001, and we switch to data view, so actually this is the number of days outside of the safety zone. So you make sure you gave the variable name as number of days outside of safety zone as 001. So just make sure you don't make a mistake when you're typing the name, because otherwise SPSS will take the variable whatever you named them as. Alright, so we're done with renaming our variables here. So these are our original zombie variables name. So first one is the number of days outside the safety zone. So you see the underscore here. Clear and straight, right? Yeah, that's something wrong with SPSS because you cannot just put space between each other. And the type is always numeric because that's how you can analyze them using most of the SPSS analyzing function. And just keep width and decimals as the default. That's because it's how it's originally set up when you open a new SPSS data file. And the label here is actually, you can put spaces. So label is actually how you're explaining each of the variable name that you gave it here. So I will personally recommend that when you do typing the variable's name under here, make it as short as possible, just for ease to use or look at under data view. But you can definitely give the full original long name under label, and that's definitely not a problem. The next column is the values. Just keep as none, missing none, and column just be let it whatever the numbers be, and align. You can change it between left to right and center, so you can definitely change that by yourself if you want. And the last most important thing is a measure. So measure here is actually they have 3 options for you to choose. They have a scale, ordinal, and nominal. And remember, we have to use a scale. Why? Because a scale means it is continuous, it is a score, and it's a ratio variable. And since all the variables in the multiple regression model are continuous, so we're going to set them all as a scale, as it says right here. All right, so now we're good to go and using this SPSS datasheet to do the rest of the questions pretty much. So let's go back to question 3. Did the data violate the assumption of normality? So we can do this through SPSS, and how? We're going to use what we called Mahalanobis distance. Bulala. All right, I'll repeat. How you check the assumption of normality for a multiple regression model? Use Mahalanobis distance. Okay, next I will show you guys how to do it using SPSS. So go Analyze, Regression, Linear, and then this little cute dialog box pop up. So here you can see that we're going to put our DVs in here and IVs in there, and then we can do the Mahalanobis distance. So first of all, what's our DV again? It's also called our criterion. Is our days left before they become a full-on zombie. So put it in here. And our IVs, which are the predictors, so it's going to be these left 2 here. Number of days outside and this stage of their zombieism. Okay, so now we're just going to check these little buttons on the right side, and I will show you how to do it, because remember, we're just checking normality, just normality. So don't run the whole model yet, okay? So go Statistics and uncheck all of this, okay? Don't include them, because remember what we're doing right now? Normality. Do I need to repeat that again? Yes, normality. Okay, hit continue. And we go plots. Why we don't need anything here? Because we're checking normality. Okay, just hit continue. And here's our star showing up. What's this? Mahalanobis. And what does it do? Normality assumption checking. So make sure you check this little box over here and hit continue. And for options, actually, we just leave it whatever it be. Even the one we're checking the whole model, you're just going to keep it whatever its default setting. So we just simply hit continue. And we're good to go. Hit OK. And remember, what we're checking right now? Normality. Good. And using what thing? The Mahalanobis distance. So here is the SPSS output. And remember, you don't need to look up any tables here, even though it says regression right here, but we're not going to looking through the whole model. And why is that? Because we're doing a normality checking. So we just need to find out where is Mahalanobis distance. Ta-da! There it is, Mahalanobis distance. And the important thing is here is that we only need to look at the maximum value of the Mahalanobis distance. And to judge normality assumptions, we're just going to compare this maximum Mahalanobis distance with the critical calculated Mahalanobis distance value. And by comparing them, we can see whether we violate the assumption of normality. So let me show you guys how to do the Mahalanobis distance critical value calculating by using the Excel sheets. It's going to be easy and user-friendly. So here is an opened the copy of the Mahalanobis distance critical value calculation Excel sheet. So this is the number we're looking for, and we're going to compare this number with the Mahalanobis maximum number in the SPSS output. So the alpha will be 0.05. As we all know, it's always the desired minimum alpha level we want. And n here is the sample size. So for our regression model is 250. And the k is the number of predictors. How many we have? 2. So just simply hit enter, and that's the number came up. It's 16.984. So apparently this critical value is bigger than the maximum value here, 12.548, which means we didn't violate the assumption of normality. So here's the answer for question 3. Next, we will check the assumption of autocorrelation, also known as independence of observation. To check this assumption, we go to SPSS, Analyze, Regression, Linear, and we just put DVs in there, days left, and the 2 IVs. So if you notice, actually this is the Mahalanobis distance score we just created by checking when we checking the normality assumption. So since we're only checking autocorrelation, so we only need the test called Durbin-Watson. So we check here, and then we're going to uncheck the other stuff which are not going to be showing in the output because we only need the tests to checking the assumption of autocorrelation. So we hit continue and we hit OK. So as you recall that autocorrelation to checking whether the participants are individualized to each other, which means each of them doesn't get contaminated. So they didn't talk with each other, which means each of them has done the task or survey by themselves. So here is the Durbin-Watson, and we only need this because we're only checking autocorrelation, and you can find the Durbin-Watson within the table of model summary. Okay, the important thing for doing Durbin-Watson test is you have to know the cutoff value of this. So your Durbin-Watson test is supposed to be 1.5 and 2.5. So if the Durbin-Watson value between 1.5 and 2.5, meaning that we didn't violate the assumption of autocorrelation. So our Durbin-Watson value is 2.092, which is exactly between the range of 1.5 and 2.5. Therefore, the data didn't violate the assumption of autocorrelation. Okay, next we will check the assumption of linearity. To check linearity, we just go SPSS and then use a scatter plot. So go Graphs, Legacy Dialogs, Scatter, and we're just using simple scatter. So click on it and hit Define. The only drawback is that on SPSS, scatter plot can only create between 1 DV and 1 IV. So since we have 2 IVs, so we're going to create the separate 2 scatter plots. So let's do the first one. So we put y-axis, which is the DV or the outcome criterion, days left before they become a full-on zombie, and let's do the first IV on the x-axis. So we do number of days outside of the safety zone. And we're set. Click OK. So here's the SPSS output of the scatter plot for the first IV or predictor. And to check the linearity, we just simply need to add a fit line so we can look at R square and to see whether the R square equals to 0 of this linear line. So we're just going to double click on the chart and go add fit line at total. So we just make sure the line is linear. And we just close all the other windows so we can go back to SPSS output. Here it is. So you can pretty much visually see that there is a slope of the linear line, which means that there must be some linear relationships happening there. But of course, the most important value to judge on is to look at R square on the right side of the graph. So the R square, as you can see, equals 0.045, which is bigger than 0, technically. So in this way, we're saying that for this IV, the linearity assumption was not violated. Now let's check the next IV. So the same thing, we go Graphs, Legacy Dialogs, Scatter, and simple scatter, Define. So we just switch the IV, take that out, put a stage of zombieism in, and we're set. Let's go, let's go, let's go, 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 go. As you can see, here's the output again of the second scatter plot for the second predictor or second IV. The DV is on the side, which is the y-axis, as you can see there. Days left before they become a full-on flesh-eating zombie. And the IV is on the x-axis. Since this is our second IV, so you can see it's a stage of zombieism. So remember, DV is always on the y-axis, and IV is always on the x-axis. Happy? You're happy?
Happy.
Okay, so let's create another fit line so we can check the R-square of these scatter plot. So double click on the chart and do the same thing. Add a fit line at total and make sure it's linear so we can close everything up. Close, close, keep closing. Oh, here it is. So you can see it's also visually there's a linear, but of course the judge, we should go for R square. And on the right side, R square equals to 0.058, which is also technically bigger than 0. Meaning for this IV or predictor, the assumption of linearity was not violated. So overall, the assumption of linearity of the data was not violated. Next, let's check the assumption of homoscedasticity. So what is homoscedasticity? It's about residual variance. So we're going to check the variance of the residuals above the best fit line and to see if they have the similar distribution of the residuals under below the best fit line. So to check that, we're going to draw what we call the residual plot. So we go analyze, regression, linear, and the same thing. Since we only need a residual plot to check the assumption of homoscedasticity. Oh, you can put the DVIVs in there, the computer. Thank you. I'm just explaining to the beloved students. So remember, we just do the same thing. We don't run the whole model. We're just checking the residual plot. So we go statistics, make sure everything is unchecked. Good. Hit continue, and we go plots. So here is where we're gonna doing the residual plot generation. So we click on Z predicted. Oh, or Z residual. Apparently, computer is just fighting against with me. My order. Okay, Z predicted. We put it to the Y. Sorry, to the X. And we hit continue.
X.
Sorry. Okay, just remember and make sure that residual is always on the Y and predicted always on the X. So sorry for my earlier mistake. Never listen to Bang Xiu. Sometimes. Okay, that's all set. And I just hit OK. Residual plot. And the same thing, we're going to add actually a straight line in there so we can see whether you can. So if you look at the chart, there's a residual dots all scattered there. So we're just going to create a line to see if they are evenly distributed above and below that line, that fit line. So double click on the chart and just add fit line at total. Make sure it's linear. Close it up. And here it is. So graphically, you can say that it may evenly distributed or similarly distributed above and below the line with each other. But just to double check and to make sure, we're going to create a line we call lowest line. Because the lowest line can give us a more accurate result on whether we violate or not violate the assumption of homoscedasticity by having the dots evenly distributed among the lines. So let's create a lowest line. So the same thing, double click on the chart and add fit line and total. So if you can see there, that's the lowest line already been checked, which means we're good to go. So just close up everything. And here it is. So if you can see that there's a lowest line in the middle, kind of like overlapping with the straight fit line. So we don't see that much of curvy happening on the lowest line, which means that we pretty much confidently saying that the data didn't violate the assumption of homoscedasticity. So for the rest of the questions, we're actually just going to run the whole simultaneous multiple regression model, and we're going to use the SPSS output to answer the rest of the questions. Let's run the simultaneous multiple regression model on SPSS. So we go analyze, regression, linear, And now we just need every possible information. So we're going to pretty much check all the things we need. So go statistics, we check estimates, model fit, descriptives, part and partial correlations, collinearity diagnostics, and then we hit continue. And we go plots. And apparently we still have the homoscedasticity residual plot created, so we can just simply hit continue. And that's all it. We just hit OK. And here's the output of a simultaneous multiple regression model. So let's start doing the questions in the Word document, and I'm going to show you which output table you should be looking at from the simultaneous multiple regression model to answer those questions. So let's do the first one. So go to the Word document, Okay, the first is the assumption of multicollinearity. So to check multicollinearity, we're going to go to SPSS output and looking for a table called coefficients. Keep going down, computer. Get work. So there it is, the coefficients table. And the computer, if you could move a little bit on the left so I can let my students see the collinearity statistics. Thank you. And that is the tests to check the assumption of multicollinearity. And we're going to use either tolerance or VIF to look it up. So first of all, tolerance and the VIF, they have the inverse relationship. So you can check either one or you can check both. And the cutoff point for tolerance is it has to be bigger than 0.1. Therefore, for VIF, remember, because they're inverse. So for VIF, it has to be less than 10. If tolerance bigger than 0.1 and VIF less than 10, that means the data didn't violate the assumption of multicollinearity. And from the table, we can see that tolerance is bigger than 0.1 because it's 0.908 for both IV. And the VIF for both IV is 1.101, which is less than 10. So that means the data didn't violate the assumption of multicollinearity. So next question is about trend analysis. And what is a trend analysis? It's checking whether the data is linear, cubic, or quadratic. So some instructors talk about it. That's why we threw it in here. And technically, trend analysis is about whether your data is linear or non-linear, curvilinear. But remember the linearity assumption, both of the IVs didn't violate it. But unfortunately, we can only check linearity for each IV individually. So therefore, trend analysis can see the big picture, meaning that trend analysis can combine both IVs and all the models together and to look at the linearity of the whole model. So we're just going to use Lewis line to do the trend analysis. Okay. So to check the trend analysis, we're just going to simply look at the Lewis line again. We just created in the residual plot for the homoscedasticity assumption. Here it is. It's not perfect, but it's relatively linear. We don't have that much of curvilinear activities going on the Lewis line. Therefore, the trend analysis, the result of the trend analysis will be the data is linear, or you can say the regression model is linear. 测试测试1 2 3 4 5 6 7 8 9 10
Right on the side. You're not funny.
Next, we're going to discuss whether the regression model is statistically significant or not. In other words, are the IVs are good at predicting the criterion? Okay, back to the SPSS output sheet. We're going to looking for an Anova table because that's the table going to give us the results of whether the regression model was statistically significant or not. And we're looking for the F value with its significant or p-value. So the F score is 10.664, and on the right you're going to see the sig which is the p-value is 0.000, which means it's less than 0.05. So in other words, the regression model was statistically significant. But remember, significance doesn't necessarily indicate whether the regression model was strong or weak in terms of predicting the outcome. That's what effect size does, and aka R squared, which we will discuss later. So we answered the question from the Anova table. We can see that the regression model was statistically significant. Effect size tells us how much of the variance of the DV can be explained by the model. Or in other words, how much of the variance of the outcome can be explained by the predictors. According to Cohen, this R squared of 0.079 is between weak and medium. Therefore, 7.9% of the variance of the outcome, which is days left before they become a full-on zombie, can be explained by the predictors of stage of zombieism and days they being outside of the safety zone. In other words, this is not a strong model, or the predictors are not good enough to predicting the outcome or the regression model.
Yeah.
Next, were both predictors significant? Let's check the output. Na. So we're going to coefficients, and here it is. So we need to look at the t-score of each of the predictors with its corresponding p-value. So if their p-value is less than 0.05, that means this predictor was significant. Otherwise, if the p is bigger than 0.05, that means this predictor was not significant. So let's look at each of the predictor. First one is number of days outside of a safety zone. And if you go to the right, looking for its t-value, that's negative 2.407. And you keep going on the right, that's the p-value, which is 0.017. And obviously, it is less than 0.05. Meaning of what? The number of days outside of the safety zone was significant. Repeat here, next here, the stage of zombieism. So we look at the t-score again. It's negative 3.026, and the p-value was 0.003, and it's even more less than 0.05. So that means both of the predictors were significant. Question solved. Moving on.
Would you be quiet?
So, which predictor was stronger will be the next question that we are concerned, extremely concerned. So, let's go to coefficients in SPSS again. Pretty much you're going to find out that you're going to use the coefficients table to talk about the individual predictors for pretty much everything. So, to check out which predictors were stronger, which are weaker, we're going to look at the standardized coefficients, also known as the beta weights. So beta weights actually tells you how much standard deviation difference it'll be changed if one unit change within the outcome happened. And you therefore, because they're standardized, so you can compare the score directly, and higher score means the predictor was stronger, predictive. Lower score means, and also make sure you look at absolute value, because negative, it doesn't mean the value, it means the direction between the predictors and outcome. It only shows whether they have a positive relationship or negative relationship. Therefore, look at our data. The beta of the two predictors, one is negative 0.154 and the other one is negative 0.194. And remember, we need to look at absolute value, which means we need to kick out the negative symbol because it doesn't mean the value, it just means the direction between the predictor and the outcome. So apparently 0.194 is bigger than 0.154. In other words, stage of zombieism was a stronger predictor of the two.
You can't hear me.
Finally, last question. So we're going to write out the regression equation based on the SPSS outputs. So let's go back to SPSS and we're going to use the coefficients table again. And remember, when writing a regression equation, you're going to use the unstandardized coefficients, also known as the B-weights. So you're not going to use a standardized, use unstandardized coefficients. Here is an example of a multiple regression equation. So we're going to substitute the constant with 53.457 in the regression equation. And then we're going to replace the coefficient of x1 or predictor 1 with negative 0.087. And also we're going to replace the coefficient of x2, which is the predictor 2, with negative 3.567. Remember, the units of these coefficients are different for each of the variable or predictor. So here is the final equation. We're done. Wahoo! Remember, these are not very good predictors. And it's not a strong regression model because of the R-squared, even though it's statistical, even though it's significant. But yeah, that means actually, if you're practically saying that, we will recommend the Lion Department of Disease Control Center to explore more predictors and then extend the regression model, trying to find out a better solution on fixing this weak regression model. So watch out for zombies. See you next time, Alliance Survivors.